The diploid organism population that we're going to work with here is wild canaries, and they do reproduce through mating. The autosomal gene that we're going to focus on is color, and we're going to represent it using two alleles, big R and little r. So there's going to be three genotypes, big R, which is going to represent red canaries, big R, which is going to represent orange canaries, little r, which is going to represent yellow canaries. So big R is our dominant allele, and little r is our recessive allele. So we have three phenotypes here, red, orange, and yellow, and our population size for this scenario is going to be 200. We're going to use three types of juices to represent our three types of wild canaries. Red juice is going to represent our red wild canaries, which is going to be represented by big R. Orange juice is going to represent our orange wild canaries, which is going to be represented by big R, little r. And then yellow juice is going to represent our yellow wild canaries, which is represented by little r. There are 32 red wild canaries, so there's 4 cups, which means that each cup represents 8 birds. There are 72 yellow wild canaries in the population, hence there are 9 yellow cups. And then there's 96 orange wild canaries, hence there's 12 orange juice cups. Based on these numbers, we can calculate the p squared, q squared, and 2pq values, which represent the genotypic frequencies for big R, little r, and big R, respectively. In order to find p squared, we need to divide the total number of red wild canaries in the population by the population size, and to find q squared, we need to divide the total number of yellow wild canaries in the population by the population size. By doing so, we get 0.16 for p squared and 0.36 for q squared. If we take the square root of these two numbers, we get p and q to be 0.4 and 0.6 respectively. So then 2pq is 0.48. P represents the allelic frequency for big R, whereas q represents the allelic frequency for little r. According to week 2 slides from Genetics 311 at NC State University, we know that if the sum of p squared plus 2pq plus q squared adds up to 1, and the sum of p plus q adds up to 1, then the population is in Hardy Weinberg equilibrium. And since our initial population does meet those requirements, it is in Hardy Weinberg equilibrium. Based on week 2 slides of Genetics 311 at NC State University, it is observed that this population goes through directional selection as the number of yellow wild canaries increases over generations. This is because the island that the birds live on is covered with white birch trees, and yellow wild canaries are the least visible to predators as they stand out the least against white birch trees. Therefore, the yellow wild canaries survive longer and go on to reproduce more compared to the other two types of canaries. According to the week 2 slides of Genetics 311 from NC State University, if a population experiences selection, then it has fitness values that indicate which genotype is able to survive and reproduce better. Since our population experiences directional selection where the genotype for yellow wild canaries is being favored over the others, we know that our fitness value for little r, or yellow wild canaries should be higher than the other genotypes. Thus, it is observed that this population has fitness values as shown: 0.52 for big R, or red wild canaries, 0.8 for big R, or orange wild canaries, and then 1 for little r, or yellow wild canaries. When determining whether or not our initial population was in Hardy Weinberg equilibrium, we had determined our genotypic frequencies for big R to be 0.16, big R to be 0.48, and little r to be 0.36. However, since this population is experiencing directional selection, the Hardy Weinberg equilibrium will be altered as over infinite generations the population will become homozygous for one genotype, which is little r, or yellow wild canaries. Because of this, we need to perform a series of calculations to account for the selection in our genotypic frequencies. In order to obtain our new genotypic frequencies, we need to first calculate the proportion of unadjusted survivors, which is proportional to the contribution of the genotype to the population while experiencing directional selection. Once this number has been calculated for each genotype as shown, we add them up to get our average fitness for the population. This number should not equal 1. And then we divide our unadjusted survivors' proportions by the average fitness to get our genotypic frequencies for after selection. When we add up our new frequencies, we should get 1 as seen. We can now use the formula shown to calculate our allelic frequencies. As predicted, our allelic frequency for little r has increased compared to the initial population's allelic frequency for little r, which was 0.6. This is because directional selection has increased the number of yellow wild canaries in the population, thereby increasing the frequency of little r in the population. So that's how directional selection affects Hardy Weinberg equilibrium. Thank you for watching.